Greetings everyone, I am Nirabhra, an MTech research student from the Department of Electrical Engineering, here to present our work titled Dynamics of a Population of Optimum Seeking Agents on a Network. Now these situations occur in lots of scenarios, and I would like to start off with a few motivating examples. The first being fleet redistribution in ride-sharing services. Here, each cab driver is an agent who is trying to maximize their own profit, and they do so by trying to service more profitable areas. The service locations form the underlying network. Another example is that study of the evolution of transportation mode choices of a population helps in future planning of infrastructure. Also, the case of the missing toilet papers in major cities across the world during the COVID-19 pandemic showed that it is important to understand the transient and asymptotic nature of social choices under disruptive socio-economic changes. Now, in each of these examples, the population is quite large, and it may be a good choice to model it as a continuum. With this choice in mind, the common thing in all of these examples is what sets up the framework. We have a population of a continuum of agents, where the agents seek to maximize a payoff function, and they do so by moving on a network. That is, agents can move from one node I to their neighboring nodes Ni. Note that the nodes represent choices here, which may be physical locations, like in the case of the fleet redistribution problem, or the choices may be abstract, like the choice of which daily essential to go for first in case of crisis. We let V be a set of nodes, E be a set of edges, and G be the underlying network. To model the system, we let Xi represent the fraction of population in node I, Pi of Xi be the payoff which each agent in node I receives, and the vector X with its ith component Xi be the population configuration. Now we are interested in the dynamics of the optimum seeking agents under different levels of coordination. For that, we propose two dynamics. The first being nodal best response dynamics, or NBRD. Here we have intranodal coordination. That is, the agents in node I revise their choices at random times, but by computing the best response of the fraction Xi to the current population configuration X. And they do so in order to maximize the payoff of the fraction Xi as a whole. The expected evolution of the population in this case is governed by a differential equation. The second dynamics is network restricted payoff maximization, or NRPM. Here we have coordination across the whole population. That is, the population evolves under a centralized decision scheme in order to maximize the social utility. Here again, the evolution of the population is governed by a differential equation. We would like to point out that in both cases, the dynamics arises by solving optimization problems, and we encountered the possibility of state-dependent switches. The results that we have obtained so far are listed as follows. Firstly, for both NBRD and NRPM with a feasible initial condition, we have shown existence and uniqueness of solutions. And both dynamics asymptotically converge to some point in an equilibrium set. Now, in the special case where for all nodes the payoff function takes the form minus half xi squared minus ai xi, we have shown the similarities of the dynamics or the evolution of the population to water trying to minimize its potential by moving across the network given by G. We have been able to derive sufficient conditions on G so that NBRD and NRPM converge to the same population configuration. And in cases where the converging configuration may not be the same, we have given bounds on the difference between the converging population configurations. Recently, we are interested in comparing NBRD and NRPM with an established dynamics in population games and evolutionary dynamics called Smith dynamics. Here, each agent selfishly revises its choices at random times, and they do so by comparing their payoff with the payoff of an agent in its neighboring node. We would like to push the framework further by first of all coming up with algorithms to efficiently estimate the converging population configuration. We would also like to come up with optimal incentives so as to control the converging population configurations. And then finally push for applications in transportation and opinion dynamics. This is a list of publications that have been generated from this work. Thank you for listening.